Okay, in the first couple of videos in this module, we took a look at vectors and sort of how to use vectors, how to use them in problems. But really, the core issue we're trying to get at in this module is how to solve problems in 2D kinematics, and all that vector stuff is really going to help us sort of break down some of the components that we need to look at in 2D kinematics. The primary problem we're going to want to look at for most of this chapter is projectile motion. So projectile motion is the motion of an object which is subject to accelerations, to the accelerations shown here, right? So the acceleration in the x direction is going to be 0. There's going to be no acceleration in the x direction. And in the y direction, this object is subject only to minus g, so gravitational acceleration, right? And so the path that any object, any projectile is going to follow is going to be called its trajectory, and we're going to be studying this projectile motion where we're ignoring air resistance entirely. Okay, so no air resistance for this chapter. We will look at air resistance in later chapters, but for now we're just going to ignore air resistance. And the key thing to remember when doing these problems is that motion in perpendicular directions, or like along perpendicular axes, can be broken up and treated as separate problems, which are somewhat coupled. They're going to be connected by the fact that time is passing the same in both of those directions. Okay, and so we're going to look at a very general sort of setup here and talk about how we might solve a problem using the tools that we developed in 1D kinematics and these ideas of vectors to solve these problems in 2D kinematics. Okay, so setting up a very general problem here. Imagine we have our x and y axis here, and we have some projectile is launched. It's following this trajectory. It doesn't matter where it ends up. It could land on top of something or hit a wall or something or whatever. But this is its trajectory. And let's give this some initial launch velocity. We're going to call this v0. v0 will have some angle. We'll call this theta 0, and some magnitude v0. Right. So we know that what this is telling us is that v0 is really v0. The vector is really v0 at some angle theta 0. Right. And the first thing we want to be able to do is we want to be able to break up this velocity into its x and y components so that we can then treat this problem as two separate 1D problems, right? And the way we do that is we use the tools that we developed in our discussions about vectors over the past two videos, and we're going to find that v0x, the x component of our initial velocity, is equal to v0 cos theta 0, and v0y is going to be equal to v0 sine theta 0, right? And so once we've done that, we're then able to treat this as two separate problems in 1D kinematics. Now we've already written down all the equations that we're going to need to deal with these problems. Well, here maybe let me call this step 1. So step 1 is generally going to be breaking up the velocity into its components. That won't necessarily be true for every problem, but you should always think about that first. Think about, well, do I have a velocity? Should I be breaking it up now? And then go from there. The second step is going to be to treat this in the form of two different 1D kinematics problems. And as I said a moment ago, we've already developed all these equations, but let's see what happens in the x direction, so in the horizontal direction, with ax equal to 0, right? That's a requirement for this problem because we're looking at projectile problems. So with ax equal to 0, well, let me start off by writing down all the old equations that we had. And I'm going to be careful here to try and include as many of the subscripts as I can to indicate that we're dealing with the horizontal direction here, because we're also going to have equations with y subscripts that are going to be indicating vertical direction for us, right? So what we have here is the equations we developed before. And finally, okay, so those are the 5 equations that we talked about in the first set of videos, right? But what happens as we set the acceleration in the x direction to 0? Well, what does this mean? It kind of also means that v0x, that v0x is really equal to vx. The velocity in the x direction is not changing, and so that means that the average velocity is equal to these things also, right? So really what this is telling us is that we can rewrite this as this equation here, and we're going to find that really all these equations are basically only giving us back this information. For example, in the case of our second equation here, v0x is just equal to vx, which is equal to v bar x, and so all this is really telling us is that v bar x, well, is equal to vx is equal to 2vx over 2, so clearly that's true, but it doesn't give us any new information, right? So we can ignore that. If we set ax to 0 here, this gives us no new information, it's just telling us vx is equal to vx again. If we set ax to 0 here, what we're left with is this equation in here, and that's really just telling us what we already know up here from this first equation, right? And again, if we set ax to 0 here, we just end up with vx squared equals vx squared, right? So this is kind of a big simplification. In the horizontal direction, all we're left with is one equation, really, and this is the only equation that we can really make use of for these types of projectile problems. Let's take a look at what happens in the y direction. In the y direction, really, we've already written down all the equations that we're going to use. We're letting our acceleration go to -g, and we looked at that in the case of falling objects in the first video series. What I'm going to do is I'm going to combine the equivalent of these two equations in the vertical direction into one equation. Sometimes that's useful. So imagine if we substituted in, well, here, maybe I'll write it out so it's more clear. What we would have is this situation, and we also have vy bar is equal to v0y plus vy over 2, right? But I'm going to combine the two of these into one equation that's going to end up giving us y equals y naught plus 1/2 v0y plus vy t, right? So that's one equation that we can use in the vertical direction. And we also have the 3 other ones that we developed before. I'll write them down again here just so they're all in one spot. And finally, okay, so in the vertical direction, we're going to find these 3 equations are useful, and in the horizontal direction, we only have that one equation that we can really make use of, right? And so this is great. We start off with step 1 up here. We break up our problem into its vertical and horizontal components. In step 2, we're sort of solving 2 1D kinematics problems. 2 1D kinematics problems where the time is shared between the two, right? So wherever we stop the stopwatch, we can sort of share that time between the horizontal and vertical directions. Sorry, that writing got kind of small there. But we'll go from there. Okay, so now step 3 is really just solving, right? So we want to find the points at which we want to answer questions about the system, and we solve for those points in time or different positions depending on what the problem is asking us. And we're going to look at an example of this right after this to sort of make things a little more clear. How much space do I have here? Okay, quite a bit. Good. So step 3. Step 3 is solve the 1D problems. And then finally in step 4, we're sometimes going to be asked to recombine this information in the x and the y direction back into something with a sort of angle, right? So we've also seen how we can do that. We can just then again make use of our ideas of vectors that we developed, where our vector a is going to be equal to a at some angle theta a, and we know that we can calculate the magnitude a from ax squared plus ay squared. And in this case, these a's would become vectors, right? So maybe I should have written them in terms of velocities, but we're going to see them. We're going to see them here in a second. Okay, so let's do an example here to sort of crystallize some of these ideas. I inserted this extra page here. I guess I didn't need to. But let's take a look at a problem. Okay, so this is an example. We have a rock that's ejected from a volcano with some initial velocity of v0 equals 25 meters per second at an angle of 35 degrees above the horizontal, and then we're told that the rock strikes the ground 20 meters lower than it was ejected. We then want to calculate the time that it takes for the rock to follow this path, and we want to find the magnitude and direction of the rock's velocity at impact. Okay? So let's solve this. First thing that I always find to be the most useful thing to do is let's just draw a picture of what we're dealing with here. So we have a volcano. Here's my volcano. Let's set up our origin of coordinates here. So that's our x direction, that's our y direction, and we're told that we have some rock being launched from the volcano, and it lands, say, over here somewhere, and we're told that this distance is 20 meters, right? This is the 20 meters lower portion of the problem that we're told, and we're also given some initial velocity where v0 is equal to 25 meters per second at 35 degrees above the horizontal. So we're told that this is our call this theta 0, and this will be v0. So this is really v0 at some theta 0, right? Where v0 is 25 meters per second and theta 0 is 35 degrees. Okay, so the first thing I would do here is I would say, well, I'm clearly going to need to break up this velocity into its horizontal and vertical components. So right away, I would go to the equations. We know that v0x is v0 cos theta 0, and v0y is v0 sine theta 0. So we can make use of those, and we're going to find that v0x, I have these calculated here. If you put in numbers, you're going to find that this is 20.48 meters per second, and v0y is 14.34 meters per second. Okay, so this is good. We've broken up our velocity, and now we're sort of set up to be able to treat this problem as two separate 1D problems. So let's think about what we're trying to do now. In part A, we want to calculate the time that it takes for the rock to follow this path. Okay, so part A, we're thinking about how long it's going to take for the rock to follow this path. Well, we can think about what's happening in the y direction, right? At y equals 0, like at t equals 0, when the rock is launched from the volcano, our y naught is equal to 0, right? We're starting at the origin. And at the end, when the rock hits the ground, our y is equal to minus 20 meters, right? Because we're going 20 meters below the x-axis here, right? So given those two parameters, and also given the fact that v0y, we just said, is equal to 14.34 meters per second, can we use any of the equations that we've developed to sort of solve for t? Well, if we look at them, we're going to find that we can. We can use y equals y naught plus v0yt minus 1/2 gt squared. We can substitute in all these values. So we know that g is 9.8 meters per second squared, and that's going to be the value for the entire course, so just remember that all the time. And we can substitute in all these values and then solve for t, right? So we substitute in for y, minus 20 is equal to 0 plus 14.34 t minus 1/2 9.8 t squared. And what do we have here? Well, we have a quadratic, right? So to solve this quadratic, and I'm not going to go through all the steps, but I'll just set it up for you guys. We're going to end up with 0. We're going to shift everything over to the right side here. And we're going to end up with 0 is equal to minus 4.9 t squared plus 14.34 t plus 20, right? It's plus 20 because we shifted the 20 over to this side. And this is what we would end up calling A, B, and C. And if we wanted to solve for t, we would end up finding that t is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And if we substituted in the values we have up here, for that, we're going to end up finding two values for t. And so we find a t that's equal to minus 1.03 seconds or 3.96 seconds. And this should be an or that kind of looks like a minus. There. And so we kind of have to think about, well, what's the physical solution we're looking for? Clearly we need a positive time. And so this is going to end up being the t that we want, and that's the answer to part A, right? So that's what we find for part A. That's the amount of time that it takes from the moment the rock is launched until it hits the ground, okay? And to get that information, we only needed to think about what was going on in the y direction there, right? In part B, we're asked what the magnitude and direction of the rock's velocity are at impact. Okay, so what we want is let me clean this up a little bit. What we want is v, and we want to find vx and vy. So where vx and vy, these scalars are the magnitudes of our vectors pointing in those directions, right? But so what do we know? We know that v0y is equal to 14.34 meters per second. We found that earlier. We also know that that the time at which the rock strikes the ground is equal to 3.96 seconds. We just calculated that. And so if we know the initial y velocity, and we know the time that it's traveling for, we can use this equation here. Vy is equal to v0y minus gt to solve for what vt is, right? Vy, sorry. And so we end up with a vy equal to 14.34 minus 9.8 times 3.96. And if you clean that up, you're going to end up finding that Vy is equal to minus 24.47 meters per second. Does that make sense? Always good to make a sort of sanity check along the way. Well, it does make sense, right? We expect a negative velocity because at the end, we're going to have a velocity vector pointing something like that, right? And so we expect the y component to be negative. Good, that's what we found. What about the x direction? Well, we already said that for projectiles, v0x equals vx equals v bar x, and we know what v0x is, so we know what vx is, right? We calculated what vx was in the very beginning, right here. So let's just copy that over. 20.48 meters per second. And so we have Vx and Vy, and really this is sort of this is really what we're looking for. We have the two components of our vector. We can just now combine them and solve for what the direction and magnitude of our vector are. Let me just sort of box these off because these are the two key results that we need. And so, well, let's combine them. So we know that V, from our earlier work on vectors, is just going to be Vx squared plus Vy squared. And this is just going to be the square root of 20.48 squared plus minus 24.47 squared. So that's going to end up being positive, obviously. And if we do that, we're going to find a V of, I have it over here somewhere, 31.9 meters per second. And as far as the angle of impact here, well, let's just call that theta. We know that theta is going to end up being tan, well, inverse tan of Vy over Vx. And if we substitute in numbers for that, I won't do the substitution, but you're basically just jamming in the negative 24.47 on top and the 20.48 on the bottom. You're going to end up finding a theta equal to minus 50.1. That's a terrible 50.1 degrees. Okay? And does that make sense? Well, we're measuring from the positive x-axis, and so that's our theta. This magnitude here is our v, and we could call this vector our v, a v vector. And so, well, that's great. So we found our answer. So our vector v, the velocity of the rock at impact, is going to be equal to v at theta, and that's just going to be 31.9 meters per second at negative 50.1 degrees. Okay? So that would be our final answer there. And that's sort of how we would go about these problems. We're going to take a look at maybe some more of these and take a look at some range stuff in the next videos. But really, this is the sort of key problem for this chapter. So this is the one you want to keep in your mind, and you want to solve ones like this. These are the ones that are going to show up on assignments and tests.